right, welcome everybody to the Center for Pedestrian and Bicyclist Safety webinar series. Today's presentation is on vehicle design and pedestrian safety. Our presenters are Dr. Nick Ferenczak. He is the Center Director here at the University of New Mexico. And we also have Dr. Chris Cherry, Associate Director of the Center at the University of Tennessee, Knoxville, and Saurav Parajuli, a PhD student at UTK. During the webinar, the Q&A feature will be available to type in questions. We will answer as many questions as possible at the end of the webinar. Our website is located at pedbikesafety.org. On the website, you can scroll to the bottom of any page to sign up for our newsletter. And don't forget to follow us on LinkedIn for the most up-to-date information. With that, I will turn it over to Dr. Ferenczak.
Great, thanks, Ben. Good afternoon or morning, everybody. So like Ben said, this is our CPBS webinar on vehicle design and pedestrian safety. My name is Nick Ferenczak, Center Director for CPBS. And I'll just be speaking briefly for a couple minutes. We've done a preliminary research project on this topic using Texas data, and then we'll hand it off to the team at University of Tennessee, Knoxville. And they'll be doing a deep dive into data from Tennessee. And then we will have 10 minutes at the end for a Q&A. So Ben already introduced our center, but please check out our website, check out our new, sign up for our newsletter, follow us on LinkedIn. And before we get into the details, I just wanted to note that the Tennessee project is part of our project number 23 UTK03. So if you go to our website, you can see more details, and that's where the final report will be hosted once that's all wrapped up. For my project, this actually predates the center, but I wanted to give credit to Olivia Tafoya, a master's student who did a lot of the data cleaning and processing and analysis. She's since graduated, but she did a lot of work behind this. Okay, so to jump into it. So the justification for looking at the impact of vehicle design, or the relationship between vehicle design and pedestrian safety, we're really interested in looking at pickup trucks and SUVs. As you can see on the right, they've become more prevalent on our roadways. So that's the share of the national fleet. You can see that pickup trucks in red have stayed about stable for the last couple generations, about 20%, but it's really been SUVs that have become more prevalent on our streets, and those have been substituting our passenger cars. So in addition to these larger vehicles becoming more prevalent, they've also been becoming larger over the last 20 years or so. So we wanted to look at both the prevalence and the size. And there's been a lot of good research out there that's looked at when a crash occurs, what are the pedestrian safety outcomes? And I think it's been pretty well established that when a pedestrian is struck by a larger vehicle, that pedestrian is probably likely to sustain more serious injuries. So what we wanted to do is we wanted to take a step back and ask, well, are those larger vehicles striking pedestrians more often in the first place? So to answer that, we derived pedestrian crash rates. So we looked at the number of pedestrian crashes per measure of exposure. For pedestrian crashes, we got that data from the Texas Department of Transportation. We wanted to look at New Mexico, but the data just wasn't there. So we looked at Texas. We looked at both total pedestrian crashes and KA, or serious injury and fatal crashes for pedestrians. And then our exposure metric was number of registered vehicles that we got from Texas DMV. We would have liked to look at VMT per vehicle, and we're still digging into some data sources, but the number of registered vehicles was the best exposure data that we could get at the time of the study. We got data back to 2015, so that was our period of analysis, 2015 to 2022. We looked at just crashes involving a single vehicle and a single pedestrian. So if there were two vehicles involved in one pedestrian, we couldn't be sure which vehicle struck the pedestrian. So we're just looking at single vehicle, single pedestrian. We can know for sure which vehicle struck which pedestrian, what kind of injury severity they had. We really took two approaches. A preliminary approach was to look at general vehicle type, so pickup truck, SUV, passenger car, and then we wanted to do a deeper dive, so we actually looked up the most popular makes and models for each vehicle type, and then we did an analysis on the make models. So onto our results. So this is looking at the frequency of vehicles striking pedestrians per the number of registered vehicles out on the roads. On the top, it is overall pedestrian crashes. On the bottom, it's pedestrian KA, or serious injury fatal crashes. On the top, the thing that jumped out to us was SUVs in orange, the top trend there. Over the study period, they were much more likely to strike a pedestrian in the first place. Passenger cars in green and pickup trucks in blue had much lower rates of striking pedestrians in the first place. And actually, the difference between passenger cars and pickup trucks was not statistically significant. SUVs rate was statistically higher than the other two vehicle types. The percent KA there, so that is a measure of injury severity. That's saying of all the reported crashes with pedestrians, how many of those resulted in a serious injury or fatality. So the pickup trucks had the highest percent KA, so they were the most likely to seriously injure or kill a pedestrian when they struck the pedestrian. So when we account for that, you can see that on the bottom graph, that blue line bumps up a little bit. So per registered vehicles out on the road, passenger cars and pickup trucks were almost identically likely to seriously injure or kill a pedestrian, while the SUV rate was still significantly higher than the other vehicle types. So for us, that was kind of the main finding for this preliminary part, what's going on with those SUVs. So we wanted to do a deeper dive. We then got into specific make and models for each vehicle type. And at this point, we broke it apart by full-size SUV, mid-size SUV, compact SUV, full-size pickup truck, mid-size pickup truck, and then passenger car. And you can see here that the top trend, the vehicle type that was most likely to strike and seriously injure or kill a pedestrian in Texas was that full-size SUV. So it was significantly higher than any of the other make models. Interestingly for us, that SUV trend was very nuanced, because you can see the mid-size and compact SUVs, the light blue trends, are all the way down at the bottom. So I think this finding adds a lot more nuance to the conversation. It's not just SUVs, it's very much full-size SUVs that we need to dig deeper into. Compact and mid-size SUVs actually had some of the lowest rates of striking pedestrians and the lowest rates of seriously injuring and killing pedestrians. Pickup trucks were kind of in the middle there. Statistically, no differences between the other vehicle types, but it was solidly the full-size SUVs that were up there. So what we did next was we took all of these crashes and put them into a statistical model, and we looked at the vehicle characteristics for each crash. So we looked at height, weight, the year of the vehicle, the year of the crash, a whole bunch of different factors for all of these crashes in our data set. And these were the results for the model. So our dependent variable was injury severity. And three things that I want to point out here. We found that all of the design characteristics of the vehicles were statistically significant. All of those design characteristics were also related to one another. So the grille height, the overall height, and the curb weight, all of those were related to one another. So we couldn't put them all into the same model. But each one was put in their own respective models, and each one was strong and statistically significant. Positive correlation, so that's telling us the taller the vehicle, the heavier the vehicle, the more likely it was to result in a severe pedestrian injury. The one other interesting finding was in light blue there. So the year of the vehicle was also statistically significant at 90% confidence, and it was a negative value. So that's saying the most recent vehicles, the newest vehicles in our data set were 2022. Those would have had a negative correlation with injury severity. So that's saying older vehicles were actually more likely to have higher injury severities. And then also at the very bottom, this kind of puts the entire conversation in context. The year of the crash was actually the most significant and the strongest variable in the model. So after controlling for all the vehicle design aspects, the age of the vehicle, everything, just when the crash occurred throughout the time period was the most important factor, the strongest predictor of the injury severity of the pedestrian involved. And the positive correlation is saying that as we move through the time period, the study period, injury severities increased. So all that is to say that vehicle design characteristics were important. They were statistically significant, but also something else is going on behind the scenes. It's a much more complex relationship. Something else is going on behind the scenes that regardless of vehicle design, regardless of vehicle year, crashes have been getting more severe for pedestrians. So vehicle design is important, but also there's other factors at play. So that was putting all the crashes through the entire study period into a statistical model. So it's basically saying the taller vehicles result in more serious injuries. That's already been proven by past research. What we wanted to look at is, are the vehicles that were getting taller throughout the study period, did those also get more severe? So that's what we're graphing here. We're looking at our 11 most popular makes and models in Texas. And the top right quadrant is the vehicles that throughout the study period increased in height. And then you can see that the severity also increased for those vehicle types. The bottom left quadrant would be the vehicle types that actually got shorter over the study period. And those vehicles also saw a decrease in injury severity. So that's showing us that not only are the taller vehicles resulting in more serious injuries, but also the vehicles that got taller over the study period also got more severe. So those are some of our preliminary results from the state of Texas. So again, kind of confirming past research that yes, larger vehicles result in more serious injuries for pedestrians, but also adding, I think, a little more nuance to the conversation, looking at the full-size SUVs, and then also identifying that trend with age, that older vehicles are resulting in more serious injuries as well. So thank you for your attention, and I'll hand it off to University of Tennessee team that did a bit deeper dive into this.
Thanks, Nick. So I'm Chris Cherry. I'm a professor in civil and environmental engineering at University of Tennessee. Saurav Parajuli is my PhD student who's doing a lot of good work in this area. And when we were talking about this webinar, Nick and I and Saurav and Ben were kind of going through the research that CPBS has done and finding a lot of interesting and, like Nick kept saying, nuanced interpretations of this vehicle design issue. So go ahead, Saurav, share your screen. So I'm going to kick off our part and show you that we are essentially going through similar types of approaches. Nick was very fortunate to have this very nice exposure variable of number of registered vehicles by type, and so he could see an extra layer of depth essentially, and understanding the pedestrian crash trends. Next slide, Saurav. Okay, so I think most of us here on the call know that pedestrian crash trends have been increasing rapidly. Here we are in 2022, up to about 18% of all traffic deaths. And that actually is a huge increase relative to the rest of the country, or rest of the modes rather. And I'll give a little preview here. In Tennessee, it's even greater than this 83% increase. We've nearly tripled our pedestrian deaths over that same period of time. And the question is why? What's going on? I think many of us have seen this graph if we've tracked the pedestrian safety situation, and it points to a lot of correlation here. The large vehicles, light trucks has gone up, light trucks and SUVs, and our pedestrian death rate, number of deaths at least, has also gone up almost perfectly correlated. And so the question is, what's the relationship, and can we track the cause of these increased deaths back to pedestrians, back to large trucks and SUVs? There's this other snippet that came from was it last month, 2 months ago, Bruce Appleyard's webinar on livable streets. And, we're not the only ones with growing vehicle size. Canada, Australia, New Zealand also have larger vehicles. The European Union, Europe is growing in their vehicle size as well, but they're not seeing this big spike in pedestrian injury and death. And so in some case, this is a unique to America problem. One thing I do want to say just unequivocally before, so go ahead, unequivocally before we move on to the next part, is that it's well proven that pedestrians' crash worthiness is not suited for any kind of car crash for the most part, and especially tall front end SUVs and trucks. So we're certainly not trying to imply that SUVs are safe, trucks are safe. They're certainly more dangerous than conventional cars if hit by one. But what we are finding is that a lot of the crash burden is still borne by conventional cars. So we'll go quickly through this. Next slide. The main thing that we're looking at here is this both the kinetic energy transfer, this is vehicle weight and vehicle speed, and trying to also control that back with injury biomechanics, essentially the size of the vehicle, and so on. We're not doing the biomechanics work, okay? We're doing the empirical work from the crash data to show that things like larger height is contributing to worse pedestrian crash outcomes, okay? There's other factors that are involved, impairment and other things that can contribute to impact speed and the like. So there's things that we're trying to control for and trying to untangle this vehicle design aspect coupled with speed and vehicle weight. So go ahead. Safe systems approach, we know this. We know that there's a lot of factors, and we know that engineers are responsible for many of these factors: speeds, vehicles, roads, even safe road users. So a lot of this falls into the, I guess you could say, the burden of transportation engineers and trying to develop solutions for these challenges. Okay, so we'll go on, Saurav. So a couple of quick points with this, and this is cited down below. You can see this kind of, I guess it might be, it's not outdated. It was 2012, but vehicles have gotten much larger since then, and this is kind of the beginning of our pedestrian safety crisis. But different types of injuries occur with different types of people. So that's one thing to consider. So we have a 50 percentile male on the top, and that person has a different crash biomechanic relationship with the middle row, which is a smaller female, a fifth percentile female. And so as vehicles get bigger, Saurav, go ahead, you can see that the crash biomechanics changes dramatically. So this is one of the mechanisms for potentially the increase in risk, the 20 to 30 to 40% increase in risk that we sometimes see cited. Okay, next. The other part is the secondary impacts. Okay, and so you noticed in those previous slides that pedestrians will often get pulled up on the hood of a vehicle for shorter vehicles, which creates different kinds of secondary impact opportunities where the pedestrian hits the ground, okay? Where the larger vehicles could potentially or often will push the pedestrian forward, and the head impact could be a kind of a more critical cause of injury or death, okay? Next. So the other part, again, getting to the nuance here is that, and we're working with Wisconsin DOT on a project related to this, is how large, tall vehicles can contribute to any number of kind of design challenges. On one side, tall vehicles could have higher visibility at longer distances over vertical curves, around horizontal curves, or vertical obstructions in curves. And in some sense, a taller vehicle does have better visibility, uh, longer perception reaction time, all of the engineering things that we may know about. On the other side, it has much more limited visibility at short distances. This is a really cool new app or website, blindzonsafety.org, and they're entering in vehicle databases and mapping the blind zones for different types of vehicles, okay? And so you might hear about the A pillar as being a potential blind zone for all types of vehicles. This is the structural support that's on the left side of the driver. This is a big blind spot for especially left turning vehicles across crosswalks or any number of kind of situations. Larger vehicles tend to have different A-pillar blind spots. They might be slightly larger A-pillar blind spots. And in this case, you have a B-pillar blind spot as well that kind of extends out. The black in this area is the ground blind zone, and the larger, the purple and other colors are blind zones for different types of vehicles. So larger vehicles tend to have kind of worse near field blind zones than smaller vehicles, even if they can see farther ahead. Okay, so perhaps a higher risk for slower speed impacts. Okay, next. And similarly, this is if you sort of extend that A pillar blind spot, you can this A pillar and B pillar, you can see that an entire section of roadway on a left turning vehicle can be obstructed at any given moment. Okay. There are interesting cases where the path of the pedestrian or the cyclist is completely obstructed for the entire duration of the curve, essentially remaining blind as the two moving objects progress through space. And this could be a situation where better design could help solve that problem. So I'm going to turn it over now to Saurav, and he's going to dive into some of the crash trends that can hopefully start to untangle some of these characteristics in Tennessee, where we've got a very rich data set, first of all, and secondly, we've had a lot of pedestrian fatalities and severe injuries over the last decade plus, and we'll hopefully start to unpack some of that.
All right. So I'm Saurav, and I'll be talking about pedestrian crash trends in Tennessee, and then the how vehicle factors, like design and A's and everything, um, kind of relate to these pedestrian crashes, right? So talking about the trend, Tennessee pedestrian fatality trends is almost like three times, have gone up three times from 2009. And then you can also see total pedestrian involved, which is also growing, but not as much, not by as much, right? And so what does that mean? Fatality trends going up, and in total involvement not going as much. So when we just divide, we get fatality rate, and you can really see, like, in 2009, 4 out of 100 pedestrian involved in crashes in Tennessee has now increased to like almost 10, which is 126% increase. So we did a simple visualization of these, like the breaking down the trends across various variables related to vehicle A's and type, and we don't see any like specific trend driving, so all of them are kind of growing overall. So maybe that suggests some other issues in play, right? But you can really see heavier vehicles having more risk to the pedestrians, kind of very slight, greater risk for pickup trucks, SUVs than passenger cars, but just from the trends only, there's very very little going on to like relate the steep rides with vehicles. And this is the type of maneuver, like how the vehicle was moving, and you can like really see the difference there between this and this. The straight maneuvers kind of tend to stick out, as you can see, almost all the fatal crash increase happened all happened for straight maneuvers, which is mostly like mid-block crashes, vehicles going not speeding, not slowing, and then hitting pedestrians at mid-blocks and stuff like that. And um, yeah, so we use police crash data. So kind of some characteristics of using police crash data is like it represents real life crash scenarios. We don't rely on simulations and other stuffs. What happened is like what we analyze, right? And then it also has some sort of injury severity spectrum, which can be more flexible in some analysis. Like we can do some ordinal regression instead of just doing some binary classification. And then it is exhaustive crash analysis, but there is this caveat that only the reported crashes are analyzed, not all, like every single crashes that occur and like in Tennessee's. And then the next thing is we can link, we have access to the VIN information from these crashes, so we can basically link the VIN data from these crashes to the standard vehicle dimensions, and even make and models from NHTSA VIN decoder and Canadian vehicle specifications dataset. And I think the most drawback of using police crash data is it doesn't have vehicle impact speed details, right? We don't really know at what speed the crashes actually occurred. I mean, we do know the posted speed limit for the vehicles, but not exactly the impact collision speed. If it was other vehicle crashes, maybe we could kind of reconstruct the whole crash mechanism and try to get that, but really this is the most drawback of using police crash data. So we use data from 2009. We use crashes from 2009 to 2024, and we used single vehicle, not single pedestrian. There could be multiple pedestrians as well, but single vehicle, non-interstate urban pedestrian crashes. So that's non-interstate urban pedestrian crashes, lots of thing going on there. And we were able to like match 16,547 crashes with the VIN, with the standard VIN decoder. A lot of misreported VINs were excluded. A lot of like super obscure vehicles were also excluded, and then we kind of retained the information for passenger cars, SUVs, pickups, and sedans. So the important consumer vehicles. And then we kind of have some proxies for analysis. We kind of established that vehicle impact speed is important, but we don't have it. So we gotta use posted speed limit as a proxy, right? although that is a limitation. And then vehicle weight. So we do have vehicle curb weights from some sort of standardized data sets, but all that is not exactly what it is. Like when a crash happens, there will be passengers. Bigger vehicle might have larger payloads and those stuff. So, but I feel like still vehicle curb weight is a very good representative of vehicle weight. And then proxy for vehicle design or front hood height. So we used vehicle over height because we don't have a specific vehicle dimension for all front hood height. We don't have that database. So yeah, something. So the rational behind that is in taller vehicles. Sorry, if you have a taller hood, the drivers should be seated at a higher position, and then for better visibility, and then that would just make the vehicle taller, right? So there is a good correlation between vehicle overall height and design. And then so vehicle A's was used for combined proxy for vehicle wear and tear effects like brake and other stuffs, and then technological advancement of safety, for newer vehicles. This is what we have for as a sort of descriptive visualization of fatality and severe injury rates for different speed limits, and you can really see some sort of situation going on, like a non-linear curve and then the non-linearity is more pronounced for fatality rate, but really like we need to adjust a lot of different factors to really see the difference between these categories. We cannot just say like passenger cars is seems to be more dangerous than pickup and SUVs just from this data. And yeah, we were talking about vehicle weight and height. So it's kind of we kind of did some histogram or some sort of density analysis, and we found this cluster of vehicle weights for our striking vehicles, which is kind of neatly arranged. I mean, you can see the peak differences, but still it's kind of clustered. But for vehicle height, you can really see the difference, like how neatly the vehicles are separated. I mean, the passenger cars is like 4 feet to 5 feet, and all of them are passenger cars. And then vehicle height for SUVs, it's kind of big area there, but really the peak for compact SUVs is around here, and then the peak for large SUVs somewhere around here. And then larger pickup trucks, smaller pickup trucks, minivans there. So our modeling approach is partial proportional odds model, kind of outcome variable, 3 levels of injury severity: fatal, seriously injured, and others. Others meaning mild injury or no injury. Independent variable, we talked about all of the important independent variables. We also included low speed maneuvers, just if the vehicle is like slowing or accelerating, slowing to a stop, accelerating from a start, or accelerating from stop, and basically turning at intersection and those stuff like that. And we also included these control variables. We'll not talk about this in this. So our results is like speed limit is strongly associated, which is obvious. A lot of studies also like relate impact speed and speed limit, posted speed limit to injury severity outcomes. But vehicle curb weights and vehicle A's are also very significantly associated with injury outcomes. we included in the independent variable, we included speed weight interactions just to like have some sort of kinetic energy situation going on. I mean, um, like um, like vehicle weight, and to kind of weigh those effects of vehicle weight and speed, right? And then it is significant. It turned out to be significant. And then so vehicle overall height is also significant for fatal outcomes, weakly significant for severe outcomes, but still a very important predictor for the injury severity. So continuing with the results, we wanted to like look at what 1,000 pounds increase in curve weight does to the vehicle injury. And then we found out that for like parking lot crashes, maybe like that occur at around 15 miles per hour, or some driveway crashes, or those kind of crashes, it is kind of significant. 13% more injury severity odds for 1,000 pound increase, but not so much for like 30 miles per hour roads, right? Only 4%. And then what about vehicle overall height? So 1 foot increase is kind of associated to raise fatal injury odds by 29 or 30%. Minivans are about 1 foot higher on average than cars based on our data set. So minivans are about 30% more likely to be associated with fatal outcomes. Compact SUV is 21% because they're about like 0.75 feet higher, taller than cars. And then large SUVs and pickups, they are really very tall, maybe up to 1.6 feet. I kind of added 42% for I mean assuming that they are 1.4 feet taller than cars, it's relates to 42%. And then what about vehicle age, right? So controlling for everything, I mean, here is a missing something, but controlling for weight, speed, height, everything. 11-year-old vehicles are 14% more dangerous than new vehicles. And why we reported 11-year-old vehicles, turns out they are the most common vehicle age for vehicles involved in Tennessee crashes. And maybe also like you can kind of assume that 11 is also some sort of time to take a vehicle to get scrapped, or some sort of time for recycle or something like that. And pickup trucks tend to be more than 11 years old. Maybe some might even go like 25 years old. And so we have these numbers, right? And we have the trends. So just looking here, vehicle curve weight is increasing, and there's no denying it. So in 1990, it was around like 35, pickup trucks were around 3,500 pounds. And then now it's almost more than 5,000 pounds on average. Similar with minivans, similar with SUVs, the green line over here. But you can see some sort of declining situation here, which is not exactly like SUVs are declining in size, but a lot of mid-sized SUVs, or Toyota RAV4 or compact SUVs kind of exploded at like 2005 to 2012. So that kind of caused the decline, but still the trend is similar. The larger SUVs is trending similar with the pickup trucks and so on. And passenger cars, although there's some slight increase, but there's a distinct increase as well. And same for the vehicle height. So same trend, almost like one feet increase in total from like 30 years ago. And then what does that mean, right? What does that mean about like for safety? And we did some sort of empirical analysis, like plugging variables to the most represented vehicle for vehicles that we have in our vehicle landscape. And um, so for residential speeds, and then compared to 2024 Nissan Altima, which is the standard full-size sedan, we can really see how the vehicle landscape had changed in terms of pedestrian severity over time. Like, Toyota Corolla was maybe some sort of is a little bit safer, was a little bit safer, and then slowly um, kind of similar to 2024 Nissan Altima. And a lot of interesting trend here as well. So Ford F-150 here, this line is really like 40% increase, 40%, it was 40% more likely to get in fatal outcomes compared to 2024 Nissan Altima. And then now it is almost 70% or 75%, something like that, which is a decent increase. Large SUVs like several suburban, even Toyota RAV4, almost 10%, and then it is now maybe 25% or so. What about EVs, right? Lucid Air, I kind of forgot to put this EV sign over here, but Lucid Air is almost 1,000 pounds heavier than Nissan Altima. So kind of 10% more dangerous than that, than the baseline. Nissan Leaf also is the same thing, but as the vehicle, Tesla Model 3 almost same. So a lot of thing is like what's going on in these vehicles is they are heavier, but they're also kind of not taller. I mean, they are shorter than the standard SUVs, right? So that kind of makes it, that kind of cancel out the effect and then kind of makes it similar. But what about EVs like Model X or Cybertruck? They're almost more than like 60-70% more dangerous than that. And we have Rivian, GMC, like way off here, which is very interesting, like in terms of vehicle weights. I mean, residential space, and you are like more than double chance of getting killed by these vehicles in residential areas. So what do we have here is like we were only accounting for this figure, we are only accounting for raw size, right? But if we account for vehicle age, then we have this sort of declining trend. I just wanted to tell this. There's a So Ford Ranger was a compact pickup truck that kind of discontinued it at around 2011. So, and they kind of reintroduced again as a mid-size pickup truck. So that kind of boosted the injury potential of that Ford Ranger. So kind of an interesting scenario to look at. And we are talking about vehicle age accounted. So if we account for the effect of vehicle age, then a lot of vehicles tend to be more safer over time. But you can see the difference between Ultima, like the sedans, and then the EVs, and then the bigger EVs, and then pickup trucks. I mean, they are kind of trending downwards, but the effect is there. Almost like, after accounting for the age differences, almost still like driving a lot of injury severity there. And what about higher speed roads? A lot of them kind of tend to get stacked together, which is very interesting. Like, what does that mean? So at lower speeds, these vehicles tend to be more dangerous, but um, higher speed, they tend to be not more dangerous. No, I mean, they are dangerous. The higher speeds is already like giving them a big boost for injury severity potential, because our base car, Nissan Altima, is already um yeah our base car, Nissan Altima, is already like driving a lot of injury there. And yeah, and then if we account for vehicle age, there is also not much difference. So it's kind of proportional increase across these vehicles, which is interesting, and like a deeper dive. That's what I did. So we have some time for questions.
We do still have a few questions in the Q&A. Would you guys like me to just go through one by one and you guys can take turns answering them?
Sure. That would be great, Ben. Thanks.
All right, we had one that came in, I believe it was when Chris was talking. It said, how do you track the change in injury severity with the change in vehicle height? Was it like tracking the percentage of severe crashes increasing for the vehicle type with a larger height?
Yeah, I think if this is for mine, yeah, we use the VIN number, the VIN for the vehicles that were involved in the crash, and I think Nick did the same thing, to assess the height as a variable in the injury model. And so I think this is a really informative infographic here, in the sense that you can apply that model to any vehicle and essentially predict the proportion or the probability of injury. And in this case, we normalized everything to a basic car. Okay. So that's the nature of that model. And so from there also you can estimate the probability of severity increase with every foot of or inch or whatever of added height. So I hope that answers your question.
All right, next question is roughly what proportion of the crashes actually had a VIN available in the Tennessee data that you used? And did you control for the age and gender of the pedestrians involved, since children and older folks might suffer more severe injuries?
Saurav, I'll let you answer.
Yes. So I feel like we had almost 30,000 crashes, and then a lot of those were like commercial vehicles. I mean, there were also commercial vehicle crashes, motorcycle crashes. We kind of excluded those because that didn't belong to the analysis, and we I think to have some sort of ballpark estimate, maybe we had to like miss out on 30% of our crash data because they weren't linkable to VIN. I'm sorry, I forgot the second question.
The second part was, did you control for the age and gender of the
Yes.
pedestrian was hit?
Yeah. Yes, we control for the age and gender of the pedestrians, but we haven't reported it in this specific study. I mean, we do have we have controlled it in our model.
All right, the next question was, says, cars are getting quieter and pedestrians are more distracted. Did you account for that?
I don't think we accounted for that. Most of the, at least in Tennessee, most of the fatalities and fatal crashes are occurring on straight higher speed roadways. So above a certain speed, I think about 25, 30 miles an hour, road noise kind of overtakes engine noise. So for EVs and others, road noise is still there. And then as far as pedestrian distraction, we didn't notice we may have distraction as an indicator for the car drivers. We're not sure about the pedestrians, but yeah.
All right, next question is, in the slide with the speeds and the vehicle make model, how does the year play into it? Is it the year of the vehicle or the year of the crash?
I'll jump in on this one. I think this is the slide that's on right now. Is that
Oh.
right? Well, hopefully this is the slide. If it's this slide, this is the year of the vehicle manufacturer. So for example, in 1994, make model Chevy Suburban is the blue line essentially. Okay, and as the year goes on, these vehicles are getting taller and heavier, and because of that, they're getting more severity in the crashes, especially at low speed, proportionally to a smaller car. So the gap between a small car and an SUV at low speeds is bigger than the gap between a small car or a regular car and SUVs at high speeds. That is, at high speeds, there's a lot more severity across all vehicles. Okay. The lines are generally increasing on the left chart, and which is indicating that the bigger weight and the bigger height is contributing to increased severity relative to a car. The story on the right-hand side is that those increases in height and weight are being essentially counteracted by the age of the vehicle. Okay, so let me see if I can say this clearly. 1994 Chevy Suburban, even though it has lower crash risk on the left side, not controlling for the vehicle age, just controlling for height and weight, ends up with higher crash risk than a 2024 Chevy Suburban. Okay, this blue line on the top, because the vehicle is potentially got maybe lower sight, visibility, maybe it has lower maintenance, lower stopping distance, and so on and so forth. So the age part is kind of an interesting piece that kind of has counteracted size and weight. The interesting and perhaps very concerning thing that we have to think about is all of these large, heavy vehicles are going to get potentially more dangerous over time as they become old, aged vehicles with less maintenance and so on. Okay.
All right,
I hope
we've got two questions that are somewhat related, so I'll summarize both of them. Was the acceleration of the vehicles considered, because there's vehicles out there now that accelerate a lot faster than they did in the past? And then the other question was, do you have any intentions to look at EVs as a subset due to their weight distribution?
So we didn't directly include vehicle acceleration as a part of our analysis, but we can argue that including vehicle age kind of somewhat accounts for that, because it really is all the technological advancements, all the safety technology, and also like the wear and tear effect of brakes and everything. So I'm guessing like we might have control for that, some sort of. And I'm missing out on the second question. I'm sorry.
Yeah, I think EV, we don't consider EVs specifically
Oh
as,
yeah.
I think as an indicator. We can include the weight of the EV, but that doesn't account for the exceptionally high acceleration of EVs. So I don't really know that. Yeah.
And for our data, we didn't account for acceleration. Good point, Roy. And yeah, Stephen, EVs. Yeah, we actually did look into a couple years of data up to 2022, and the sample sizes were still just too small to get any statistically significant results. So we started it, and we don't quite have strong enough results yet. But yeah, it's something I'm looking forward to. Hopefully within the next couple years, we'll have enough data, enough pedestrian crashes with EVs, at least for the Texas data we looked at, that we can actually say something with confidence.
All right, just a few more minutes here. Let's try to squeeze in some more questions. Did you consider the location of the crashes used for the analysis? Like, were they mid-block or at an intersection?
Um,
Yes, the answer is yes. Mid-block and
yeah.
turning movements, low speed
Yeah.
maneuvers were included. Most of the one of the graphs, I don't think it made it on this, were the bulk of crashes were mid-block. The bulk of the growth of the fatal crashes that we saw over the last decade were mid-block multi-lane arterials.
And we did not. If Olivia was a PhD student, we would have dug deeper, but yeah, we didn't quite get there for our analysis.
All right, let's see. So you have a question that says, the age of the vehicle also makes the safety issues that become standard a change to note. Did you normalize it based on safety regulations or policies?
So the age of the vehicle is kind of a tricky variable, and we've grappled with that, at least on our side, quite a bit. The most important challenge, I think, is we're maybe speculating that the age of the vehicle, an older vehicle that is being more complicit in severe crashes, is because of braking or other things. We also have to understand that people who drive older vehicles are maybe driving them in different ways. They have different education or other sorts of demographic variables that contribute to crashes as much as the vehicle itself. Now, so we don't know the causal line, I guess you could say, for why older vehicles are implicit in crashes. We are doing some of that work with this, what we call the so-called home-based approach, where we try to grab some demographic variables from drivers' census tracts and census block groups, along with the pedestrians for that matter, and trying to understand how to add this sort of, or at least control for this host of demographics that may contribute to older vehicle crashes or newer vehicle crashes for that matter. A lot of these newer huge trucks are luxury machines essentially, so that contribute, there's a whole different control variable there.
All right, and it is about 1 o'clock, so I'll let you guys have any parting words if you have any. Otherwise, we will end the webinar here.
I guess just thanks everybody for attending the webinar, and yeah, check out the Center for Pedestrian and Bicycle Safety website for other upcoming webinars and